Okay, let's do our usual test. Make sure the audio's good, and then let's get going. Sounds like it is. Excellent. All right. So today we are getting back into 5.1. We're going to actually finish 5.1 pretty quick today, and then we're just going to go straight into 5.2. So I had originally intended to just do Monday, Tuesday, kind of back-to-back recordings this week and try to just get everything done right away, since I won't be able to record on Friday this week. However, life happens, and I was not able to record last night. So we're just but luckily it shouldn't be a problem. We're just basically gonna get through what we can today, and then we'll only have 2 this week. Nothing on Friday. You had a tough one with the exam last week, so why not take one off, right? So we'll take one off there, and then we'll get back to it for the last week of class. We'll finish up, and then we'll be done. Amazing. So let's get back into this complex analysis story, see what we can do. Real quick, last time we were talking about conformal maps. These guys are just, they preserve angles, at least relative to tangent vectors of curves intersecting each other under the image, right? And they just stretch things out and rotate them, essentially, at least locally, infinitesimally, near a given point. That is what they do. Near a given point, they just act like a rotation and a stretch, and that is the deal. So what we first started out by doing is saying, hey, okay, so what maps are conformal? Well, under our definition, it turns out to be very easy. The maps that are conformal are the analytic maps with non-zero derivative. So if you have an analytic map, all you have to do is go, okay, this is analytic. Now, if you want to know if it's conformal, you just check whether its derivative is 0 at that point. Then that tells you if the map is conformal at that point. If you can calculate all of the places where the derivative is non-zero, which is equivalent to finding the places where the derivative is 0 and then taking its domain of analyticity and subtracting those places where the derivative is 0, this will give you the domain of conformality, like the maximal domain of conformality for that map. Fair enough, right? Okay, so conformal maps, and just to be clear, it's not the case necessarily that at points z0 where f prime is, say, 0, right? It's not the case that those things are like simpler than a conformal map or something. It's not the case that nothing happens there or something. It just is in general the case that it's more complicated than this picture. So when you think of analytic functions, don't just think of conformal maps. There can be more complicated and interesting things going on. However, those things happen at the places where the derivative is 0. So analytic maps are conformal everywhere that the derivative isn't 0. All the really interesting stuff happens near the places where it is. All right, cool. So we started exploring what conformality is all about. We said, hey, if I've got 2 sets A and B and we've got a conformal bijection between them, a 1-to-1 and onto map between sets A and B, then the inverse of that map is also conformal. All right, fair enough. We also said if we have 2 conformal maps, bijective conformal maps, then their composition is also a bijective conformal map. So this says that conformality is the conformality of bijections is preserved under inversion and composition. Nice. Says that they play well together. Okay, easy. Then we started to get into the more interesting stuff. We got into the Riemann mapping theorem. So the Riemann mapping theorem started with a connected and simply connected region that wasn't an entire complex plane. So you just have to go, it's not the whole dang thing. All right. What we ended up getting, starting with this region, is that there exists a bijective conformal map from that region, that simply connected region that isn't the entire complex plane. There's a bijective conformal map from it to the open unit disk, centered at 0. Unit disk, regular old unit disk. Now, even better, for any fixed point in A, in that simply connected region that isn't the entire complex plane, you can find a conformal map that takes that point to 0 and has a non-zero derivative at that point. Fair enough. Okay. I mean, the non-zero derivative at that point is a little bit unnecessary, given that for all intents and for our situation, analytic and non-zero derivative is just, it necessarily must have a non-zero derivative if it's going to be a bijective conformal map, right? Okay, fair enough. If it's analytic, it's got to have a non-zero derivative to be conformal there. So this is kind of obvious, but ultimately it is unique, at least with the specification, in fact, that at that point the derivative happens to be a positive number greater than 0. We talked about that a little bit last time, but we'll essentially gloss over that for the moment right now. Now, the thing that we were doing next was we were saying, okay, so any region A connected, simply connected, not the entire plane, we can map it conformally and bijectively to the open unit disk. So if we have two different connected, simply connected, not the entire complex plane regions, A and B, we could map both of those guys into the disk. And since we can do this bijectively and conformally, and since the inverses of conformal bijections are also conformal, this gave us a way to go from one to the disk and then from the disk back to the other across that map that took that one to the disk in the first place. So this gave us a way to say, okay, hey, I can make what this is we got the idea of conformally equivalent. We said that things are conformally equivalent if there's a bijective conformal map between them, two regions, right? So the Riemann mapping theorem says that two connected, simply connected regions that are unequal to C are conformally equivalent. That is, there's only one equivalence class of connected, simply connected regions that aren't the entire complex plane. They're all conformally equivalent. Okay, interesting. So we got to our next useful fact, which led into some cool theorems. This one is that if you have A and B, two connected regions with boundaries, boundary of A and boundary of B, denoted BDA and BDB, then if F from A to F of A is conformal, and if F of A has boundary the same as B, and for some Z in A, F of Z is in B, then F of A is equal to B. That is all we have to do to tell whether or not a conformal map from a connected region to another set, whether that is a given set, is to say, hey, do we get the boundary from the image and is at least one point inside? So you've got, like, I'll draw it like this. You've got A over here and all the stuff in here is A, right? I'm drawing the edges all squiggly, and then F is going to map that over to some other thing B, or actually here, let's even say this. It's going to map it over to F of A, how about? And that's going to be something, right? Now, if we want to know whether or not F of A happens to be B, now how I'm drawing it is already giving away that it's going to be. All we have to do is tell whether or not the boundary of F of A, if, say, this thing here is its boundary, then having a single point here go to inside of it means that this whole thing is just F of A, right? So all you have to do is go look for the boundary, and then, hey, well, the entire inside of it, as long as one point goes there, everything goes inside of it. Interesting. And it actually fills the entire thing in. So that's pretty cool. That is a pretty neat fact. All right. Let's, ooh, I drew that on the background. Oh, crap. I've made a terrible mistake. Here, let's erase that. Oh, well. Bam. Easy. All right, good. So from there, this was how we were ending things last time, pretty much. We went a little tiny bit further. So after this, we said, all right, so the Riemann mapping theorem tells us that the behavior on regions for open connected sets is nice relative to conformal bijections. That is, as we said with the Riemann mapping theorem, then you can always take a connected, simply connected region that isn't the entire complex plane and map it into the disk. And since you can invert these mappings that you get, they're conformal bijections, you can map any connected, simply connected region that isn't the entire complex plane to any other connected, simply connected region that isn't the entire complex plane, and you can do so conformally and bijectively. Now, this gave us something nice, which is all about the boundary stuff. And the Riemann mapping theorem does not say what happens on the boundary of A or on the disk, or of the boundary on A and the boundary on any other region that could get mapped to the disk or something like that. So this is an important question to ask. One of our initial pieces is the Osgood-Carathéodory theorem. It is an important theorem, and it is a nice one. It says that if A1 and A2 are bounded, simply connected regions, whose boundaries gamma 1 and gamma 2 are simple continuous closed curves, then any conformal map of A1 that's 1-to-1 onto A2, so bijection, can be extended to a continuous map of A1 union gamma 1, 1-to-1 onto A2 union gamma 2. That is bijection. Okay, so since A1 union gamma 1, that's just A1 union the boundary of A1, and that's the closure of A1. Same business over here. This is just the closure of A1, and this is the closure of A2. Okay, so we're saying that if we have a bijection from A1 to A2, a conformal bijection, then we get a conformal bijection from the closure of A1 to the closure of A2. Nice. It's pretty good. Okay, so this is a nice thing. Okay. So this gives us continuity. Sorry, I should be clear here. We don't automatically, I just lied to you really quickly. I said that it extends to a conformal bijection on the closures. It extends to a continuous bijection on the closure. So conformal map A1, 1-to-1 and on to A2, extended to a continuous map. So once you've got this continuous piece, we can get a whole lot more. And this is the theorem that we were going through last time, and I thought that we were missing a lemma that was a little bit before this, and then I realized that I just needed more sleep and was an idiot and wasn't thinking, oh, I didn't miss a lemma here that we needed. I just didn't realize an obvious fact. So what we'll go back through this now and we'll finish off the proof. So in theorem 5.1.6, we said, hey, we've got a bounded region. Why will this be important? Well, because if it's bounded, then when we close it, it'll be compact, right? Compact is closed and bounded. It's the Heine-Borel theorem that we talked about in section 1.4, I believe. So with f from A to f of A, a bijective conformal map onto the image, of course, f of A. So we're going to suppose that f extends to be continuous on the closure of A. That is, we're basically in this Osgood-Carathéodory theorem business, right? And the f maps the boundary of A onto a circle of radius r. So we're going to say, what we're going to claim is that f of A equals the inside of the circle. Okay, so f sends A to f of A, and it extends to a continuous map on the closure, and this continuous map maps the boundary of this closure, right? The boundary of A onto a circle of radius r. Okay, so this means that, hey, you've got A, and out here you've got boundary of A, right? Oh, I should have done it with the lowercase b, whatever, boundary of A. Okay, now if f sends this guy to a circle of radius r, So if this is f of boundary of A, then what we're claiming, if it does this in a nice continuous way, f extends to a continuous map from the closure of A, which is A along with its boundary. If it extends to a continuous map, and then this extension maps the boundary of A over to the boundary of the circle, then A gets mapped to the inside of the circle, and in fact equals the inside of the circle. Now, using exactly the same argument we did before about saying, hey, if we can always map to a circle, and we can do so in a nice way, then we can map between different things. There's nothing fancy here about it being a circle. In general, in fact, if B is a bounded region, I keep writing on the background, if B is a bounded region that together with its boundary can be mapped conformally onto the unit disk and its boundary, and if F maps the boundary of A onto the boundary of B, then F of A is equal to B. So really this is saying there's nothing special about this being a circle over here. This could be a much squigglier shape and it wouldn't matter. All right, so that's the whole business, and that's in fact how we'll start out. We said, hey, by composing F with a conformal map H that takes B to the unit disk, it's sufficient to consider the special case where B is equal to the unit disk itself, right? So if we can always go to the unit disk, then we can do the exact same thing and go back, right? With the whole bijective conformal map business, right? Okay, so we're just going to assume that B is equal to the open unit disk centered at 0, right? So on the boundary of A, the modulus of f of z is equal to 1. Why is that? Well, it's because we're saying that f extends to be continuous on the closure of A, and it maps the boundary of A onto the boundary of B, which in this case is the open unit disk. And what is the modulus of something on the boundary of a disk of radius 1? It is 1, right? Disk is centered at 0. Everything on the boundary is in fact all of the points that have modulus 1 in the complex plane. So by the maximum modulus theorem, remember the maximum modulus theorem says that a analytic function hits its maxes on its boundary, right? It doesn't hit them inside the boundary, right? So it means that in modulus it's got to be less than or equal to 1 inside the boundary, which is on A. So f of z is less than or equal to 1 on A. Now f isn't constant, so f of A is contained in D, right? Because we have to actually hit 1, right? And f is indeed not constant. It has non-zero derivative, right? So the interior is in fact contained in there, right? All right, fair enough. So non-zero derivative, it's got to be, it's got to vary somewhat at some point. It can't just be exactly 1 everywhere. Otherwise it would have a 0 derivative. So it's got to be less than 1. So f of A has to be contained in D. In other words, at no z in A is the maximum reached, right? Since we could apply this argument to some smaller chunk, right? Okay, so f of boundary of A is the boundary of the disk, so that is just all the points of radius, or the points on the boundary of the circle of radius 1, right? These are all the points with modulus 1, right, in the complex plane. But notice f of the boundary of A is also equal to the boundary of f of A now, right? Why is this? Well, since A is a bounded region, the closure is then closed and bounded, right? So that's compact. And since the continuous image of a compact set is compact, and f extends to a continuous map on the closure, this means that f of the closure of A is indeed compact, right? So the closure is D intersect boundary of, f of the closure will be, it's exactly, we're just breaking it down like this. The closure of D is, the interior of D is, I'm getting ahead of myself. So obviously D intersect its boundary. Since D is open, it doesn't contain any of these boundary points, right? So that's empty. Similarly, the f of A intersect its boundary is also 0, since we showed that there are no z in A where the maximum is reached, right? Since the boundary consists only of points with modulus 1. So those are both 0, right? Or empty set at least, right? Set 0. So we've got at least one point inside, and boundary of f of A is equal to the boundary of D. So by this nice theorem, or by this nice fact right here, right, that f of A has boundary same as B, and some point is in it, then f of A is equal to B. We got that automatically. We didn't even have to assume there was actually a point in there. We just got that there was one, right? Just from this piece. Okay, cool. Easy enough. So all you have to do to say that if you have a bounded region, if you have two bounded regions, A and B, and let's assume that B can, together with its boundary, be mapped conformally onto the open unit disk and onto the disk and its boundary. Then if we want to see if these are bijectively conformally, or if they're conformally equivalent, that is, if there's a conformal bijection between them, all we have to do is see whether or not there is a function f that from A to f of A that maps the boundary, that extends to a continuous map on the boundary and maps the boundary of A onto the boundary of B. So it just has to go from boundary to boundary. Easy enough. All right. So all of this feels relatively abstract right now, and this is really the main content of 5.1. So let's start into 5.2 and start seeing a little bit better examples of what various give us more room on the screen. I didn't realize I had my layers palette up. What various conformal maps are really like, or at least what nice classes of them are like, since we know that they're really just the analytic functions with non-zero derivative at a given point, right? A nice thing to do might be to ask, hey, what are some particularly convenient ones? That is, for example, what are the conformal maps from the disk to itself, or the bijective conformal maps from the disk to itself? That is, how can I map, what are the self maps, the bijective conformal self maps of the disk? I mean, there obviously are some. For example, the identity function, f of z equals z, right? Okay, but there are more. Now, what are they? Oh, almost sneezed. Okay. Fighting off that sneeze for a minute there. What are they? All right. So we're going to start investigating specific conformal maps. In particular, we're going to talk about fractional linear maps and Schwarz-Christoffel transformations. People also like to call these fractional linear transformations. We also call them Mobius transformations, though that name does appear elsewhere in mathematics, so some people don't like to use it and instead say this. All right, so now we're gonna be able to get some nice things here that'll make it so we can handle a lot of useful situations. Let's start it out. So fractional linear transformations, one of the simplest, most useful ones, also called Mobius with the O with the umlaut on it. These are mappings TZ of the form AZ plus B over CZ plus D, where A, B, C, and D are all complex numbers. Okay, fair enough. Now, why? We're going to also have to assume that AD minus BC is non-zero. Why are we going to assume that? Let's do a quick calculation. So, A, B, C, and D, fixed complex numbers. This is the form we're going to have all of our things take. We're going to assume that AD minus BC is 0 because otherwise I'm going to claim T would be constant. Why is this? Let's write it out. So if we have, in this case, I'll just keep writing it right here. Actually, I'll go off to the side a little bit. So if AZ plus B over CZ plus D if AD minus BC is equal to 0, that's another way of saying AD is equal to BC, right? Then let's multiply the top and the bottom by C. How about CAZ plus BC over C times CZ plus D. How about? Okay, notice now BC is equal to AD, so I have CAZ plus AD over C times CZ plus D. And hey, wouldn't you know it now, I can take this guy up top and pull out an A. So I have A times CZ plus D over C times CZ plus D. And bam, bam, cancel. This is just A over C. Huh. Whoa. So it's just constant. Okay, so we'll omit the case AD minus BC is equal to 0. We're going to assume that it's not, because otherwise we have just a constant. I know that's seems like a confusing statement at first, but all you have to do is multiply on the top and bottom by C, and it just falls right out. Okay. So let's begin to discuss what these guys do. However, before we do that, I think it is useful, and your book doesn't really do this, though I think it makes it make a lot more sense. Let's take a moment really quick and try to explain what a transformation TZ of this form actually does. AZ plus B over CZ plus D. Okay, now I'm gonna write a few functions here really quick. F1 of Z, which I will say is Z plus D over C. F2 of Z, which is 1 over Z. F3 of Z, which is the most interesting, BC minus AD over C squared times Z. And then finally F4 of Z, which is Z plus A over C. Okay, so these four guys, I'm going to claim you can put together and make into TZ. So I'm going to say actually that you can just plug all these guys together. It's F4 composed with F3 composed with F2 composed with F1 of Z is equal to this. So what are these pieces? And this I'm not going to make you like verify this or something. I'm just trying to explain what this transformation does. It is like a really pretty simple, if you look at it, transformation. It's just linear over linear. Like, oh, yeah, sneeze. It's just like a ratio of lines, right? But trying to understand this in terms of some easy to visualize things is sort of useful. This basically says that you only have a few steps. One of them is just translating. So shift Z over by D over C. Since these can be arbitrary complex numbers, we can just move these guys around. Okay, all good. So we're going to move this over. This, by the way, this only holds obviously if C is non-zero, right? Okay. If C is 0, then notice this is just A over D, Z plus B over D, right? It's just a linear map, and that's super easy to understand. So if C is non-zero, this is not a linear map, and it instead is a little bit more interesting. So if C is non-zero, then the first thing that T of Z, this fractional linear transformation, does is it just shifts Z over by D over C. So if we kind of draw something right here, it's like, okay, you've got Z, and then in step number 1, we're going to like move this over a little bit. And it's harder to see just for a single point for certain steps here, but this is like Z plus D over C or something. Now, the next step is that we flip this 1 over Z. This is just reflection, right, with respect to it just flips it around, right? So if like you had, you know exactly how that looks, right? How the graph of, 1 over X looks in the real line and all that. We're just essentially doing inversion, here we have pictures. Actually, I have pictures here that'll make this a little bit easier. I have a better picture. Well, this is not a great picture. It's gonna be a terrible picture, actually. Well, you do have nice, fun pictures of inversion, stuff like this. But basically, just think of like how the Riemann sphere looks, right? That's what I was going to start to try to draw, but it will look bad. The idea is that, like, you know, if you have, think of the sphere, the Riemann sphere that we were drawing for a while. It's a terrible sphere. I'm so sorry for how bad of a sphere this is. Here's the gist. So that's the part that's behind it. If down here is like 0 and up here is like infinity, right? And this is the line, you know, mod z equals 1, right? Then this boundary of the unit disk, when you invert it, when you take it to 1 over z, it's still, everything on there still has modulus 1. However, stuff that's really close to 0 gets really close to infinity, right? Well, stuff that's quite close to infinity gets quite close to 0. So we're just turning the sphere inside out, right? It's just flipping the sphere inside out. That's exactly what's going on right here. So whatever point is on one side, it's like you turn the dang thing inside out, and now it's on the other side. So it's like stuff here is getting mapped to stuff, you know, like up there or whatever, right? Just turn it inside out. All right. So that's what's going on there. It's not quite as easy of a picture to draw as this one where you're just moving it. This is what F1 stuff looks like. This one, we're just turning. We're turning it inside out, right? So just like pull that 0 and the infinity, like switch them out. Like imagine like taking like a balloon and grabbing the inside of the balloon and pulling the balloon inside out. Okay. Now F3 is one of the more difficult to understand pieces. This one has a nice picture, but it is probably something that I am guessing most people have not heard of before. It's a type of transformation called a homothetty. So homothetties are basically like, okay, there's some fixed, you know, vanishing point, if you want to think of it like that. And what it does is it dilates stuff with respect to that vanishing point. This is like what you did probably back in, like, I don't know, like in middle school art class when you learned how to draw like a 1-point perspective, right? The transformation that takes something like A, B, C, D, E here to A prime, B prime, C prime, D prime, E prime. This is just a homothetty. Okay. So the next thing that happens is homothetty and rotation, since we are chilling in the complex plane. Now, the rotation piece here is basically just saying that that homothetty can get moved around a little bit. And in fact, let me just grab that homothetty image and paste it. It's not. Is it gonna work? Yep, there we go. Oh, it's not gonna work that well, is it? Can I invert it? There we go. Okay. That'll do it. Nice. Okay, perfect. Now we're back to where we want to be. So this is F3. And this piece here is this is what's going on there. So it's only easy to visualize for like sets of points. For individual points, it's kind of like what the heck kind of transformation, right? But it maybe rotates, you know, and does this, right? So it'd be like this piece goes like out like a homothetty, and then that eventual piece you get maybe ends up rotated, right? So that's the next piece that happens. That's F3. And then the final piece is just, well, it's another translation. It's Z plus A over C. Okay, so F3, this is what's going on. And the final one is yet another translation. So basically move your point some amount, then we're gonna flip this Riemann sphere inside out. Okay. And then we're gonna do a weird homothetty kind of grow or shrink shapes according to a 1-point perspective. Do a little rotate if we need to, and then move things one more time. That's all. Kind of cool, right? It's a neat little trick. So it's like if you had, you know, like a shape here, right? If Z was part of a shape, like a little box, then the next thing that happens is it just gets moved on, over. I'm drawing that box again horribly. Okay, and then you've got your little box here, and it gets flipped inside out and ends up as a box up here. Then this box up there gets, like here, you know, some point, it gets mapped up to a bigger box, maybe rotated a little bit around in the complex plane, like you turn your axes a little bit. Okay, and then finally it gets moved one more time and you're done. So this is sort of the visual way to think of what these guys do. It just shift, flip inside out, do a 1-point perspective, and then move it one more time. All right, cool. So back to our regularly scheduled programming here. All right, so we're gonna start to investigate the properties of these fractional linear transformations and see what they do. All right, the map T, as we defined it just before, that is this fractional linear transformation, is bijective and conformal if you take it as having a domain A equals Z such that CZ plus D is non-zero. That is the not singularities of this guy, right? And they're all simple poles, right? Okay, that is when Z is not equal to minus D over C. It sends that set onto the set of complex numbers omega such that omega is not equal to A over C. Notice that's what we got out in the case where AD minus BC is equal to 0. That's what that transformation is, just a constant right there, right? Okay. The inverse of this guy from these sets also exists is a fractional linear transformation and is given by T inverse of W is minus dW plus B over CW minus A. That is, it is yet another fractional linear transformation. This is like A prime, you know, W plus B prime over C prime W plus D prime, right? If you just relabeled these guys, notice you've just got exactly the same form as what you have up here, just with some different values. So this is also nice. This says, hey, these maps are bijective conformal maps on the appropriate domains, and they have conformal inverses that are also fractional linear transformations. So it's even better than just having a conformal inverse. It's a conformal inverse of the same form. So that's pretty cool. Okay, now if you guys will buy that this thing is obviously analytic on the set of points where the denominator is non-zero, and then you'll also buy that if this is the inverse, then that's also going to be analytic on the set of points where it's non-zero. Okay, so T is definitely analytic on A. We can buy that. And this function that we're going to claim is the inverse is also analytic on B, since the bottom CW minus A is non-zero precisely when W is not equal to A over C, right? Okay, so that's analytic on B. The map T will be bijective if we can show that T composed with S and S composed with T are the identities, since this means that T has S as its inverse, right? Okay, so all we have to do is go through and plug everything in. So if we take T and we plug in S, so A times that entire fractional linear transformation plus B, C times that entire fractional linear transformation plus D. Just do the tedious calculation. A times minus dw plus BA, right? Plus, and then we just have to get common denominators and all that stuff. Notice when we can use CW minus A as denominators on both of these guys, so we'll just end up with A minus DW plus BA plus B times CW minus AB. That's just going to be the numerator from up top, right? We put this all into one fraction. And then we do the exact same thing down here, and notice since they have the same denominator, those denominators will cancel when we flip and multiply. And so we just do the exact same thing, C times minus DW plus B times C plus D times CW minus A times D. Hey, that's what we have on the bottom. Now we're just going to go through and do a little bit of simplification. So we're going to pull out a W since we've got W's in a lot of stuff here. We've also got these ABs and this minus AB, right? Okay, so we're going to pull out some stuff. We get BCW, so BC minus AD, and we got the W that we pulled out. Okay, good. Now on the bottom, we have BC minus AD. Notice BC minus AD, since I have a minus CDW and a plus DCW, those guys just reorder, cancel each other out. And hey, wouldn't you know it, BC minus AD, BC minus AD, cancel, cancel, just get W. All good. Now why can we cancel there? Because CW minus A is non-zero, and because BC minus AD is non-zero, right? CW minus A was the common denominators between these guys that we ended up canceling out before. That's non-zero. And then by assumption, BC minus AD is non-zero, right? So if we do exactly the same kind of calculation again, but now we plug ST into S, I claim that we'll also get that. You can go through and verify that independently if you want. It's essentially the exact same calculation. Just switch out every, like switch out these two guys. You can pretty easily see that exactly the same thing will happen. Now we're going to finally claim that T prime of Z is non-zero. And this is a great piece of this to notice if you're still trying to do the last problem on tonight's homework. Basically the same argument you're going to use there. So notice if you take ST and you ST Z is Z, just do DDZ on both sides. DDZ of Z is 1. Well, it's going to be the same as DDZ of STZ. And if you do that using the chain rule, S prime of T of Z times T prime of Z. So if that's equal to 1, T prime of Z cannot be 0, right? 0 times something is never 1. Easy enough. Okay. So it's non-zero. It's analytic. It is the inverse. So non-zero and analytic definitely is conformal, right? Bada boom. All right. Cool. So we proved that. Now this tells us that on appropriate domains, fractional linear transformations are conformal bijections, and they have inverses that are also conformal bijections and fractional linear transformations. Now, what we're going to claim, and this is why we even care about these guys at all, is that I'm going to claim that any conformal map of the open unit disk onto itself is a fractional linear transformation of the form Tz e to the I theta z minus z naught over 1 minus z naught bar z. That's a bar up there if that's not clear. Hopefully that's visible, but just in case it's not, that's a bar. Okay. For some fixed z naught in the disk and some theta in 0 to 2 pi, not including 2 pi. I hate that they do the reversed bracket in this book. That's the worst notational convention. And moreover, any T of this form is a conformal map of D onto D. Okay, so any T of this form is a conformal map, and if you have a conformal map of D onto itself than it is of this form. These are all of the conformal maps of the disk to itself. Huh, crazy. All of the maps from the disk to itself just look like these fractional linear transformations, and not just fractional linear transformations, but this particular nice type, this little subset. It's e to the I theta, which is just, think about like, rotate stuff, right? Okay. And then z minus z naught 1 over z naught bar 1 minus z naught bar z. All right, cool. So let's prove this. This is a interesting one to try to prove. So, just realized we don't have any more music, and that's strange. Okay, good enough. That's relaxing. Okay. So the first thing we're going to do is we're going to check that for a t of this form, so this guy right here, modulus z equals 1 implies that t of modulus z equals 1. Okay. So we're going to make sure that it sends the boundary to the boundary, right? This is exactly what we started with, talking about how, hey, if we have a nice conformal bijection maps boundary to boundary, conformal map maps boundary to boundary, then it will send, if it extends to something that maps from the boundary to boundary. And so indeed, if it does map the boundary to the boundary, then it maps the inside to the inside. Okay, so we'll check that modulus of t of z is 1. Indeed, if you just go through and do it, notice that e to the I theta, that's obviously got a modulus of 1. And if we do this, we can split it up as z minus z naught modulus z inverse minus z naught bar. But modulus z is 1, and so z inverse equals z bar. Why is this? Think about it. It's because, if you don't remember this formula, z bar is equal to modulus of z squared, right? So z equals, or z inverse equals what? It's going to be, sorry, I'm making a terrible, ridiculous mistake right here. It's a z bar over modulus z squared, right? Or is there not a square here? That's what's throwing me off. There's either a square here, there's not. If I'm making a dumb mistake, my apologies. It doesn't make any difference in our calculation right here because modulus of z is equal to 1. So in this case, this tells us that the inverse is equal to its conjugate, right? Okay, so if the inverse is equal to the conjugate, then this guy has the same modulus as z, and of course we just end up with, here we have z minus c naught over z bar minus c naught bar, so that is just the conjugate of both of those guys. And since the modulus of a complex number is equal to the modulus of its conjugate, right? It's just, if you're here in the complex plane, and here's like the real axis, right? And you just flip to right down here, just turn the imaginary parts negative, those arrows have the same length. Okay, so modulus of conjugate, same as modulus of not conjugate. And so since z minus c naught, or z conjugate minus c naught conjugate is just the conjugate of z minus c naught, these guys are the same, and we are where we want to be. The modulus of something on the boundary under t is equal to 1. So it's on the boundary of the image, okay? Or at least it's on the boundary of what we want in the image, the boundary of d in the image. So now we're gonna go, okay, we're gonna talk about the only singularity. There's only one singularity of t. It's at z equals z naught bar inverse, right? So if you take z naught bar inverse times z naught bar, you'll get 1. 1 minus 1 is 0, right? Okay, so that's the only singularity, but z naught bar inverse is outside of the unit circle, right? for some fixed z naught in D. Okay. Notice if z naught is, say, like 0 or something like that, then you could think of this as being like, like the infinity point on the Riemann sphere, right? Since inversion is basically just turning that sphere inside out, right? So turn that guy inside out and you go to the infinity point, but pick anything. Basically what we're saying is that if you have the Riemann sphere with 0 at the bottom, infinity point at the top, terrible infinity, and then this boundary right here is all of the points with mod z equal 1, or modulus of z equal to 1, then everything down here obviously gets mapped onto all of the stuff up top here when you flip it inside out, right? So nothing stays in there. So, okay, cool. So that's outside of the circle. All right. So from exactly the same kind of thing we just did right back in 5.1 right here, right? We've got two bounded simply connected regions. In fact, we've just got we're even in a slightly better position than we were in 5.1.6, where we just had a bounded region and some bounded region that together with this boundary can be mapped conformally onto the unit disk. Well, heck, we're dealing with the unit disk, so obviously it can be mapped onto the unit disk, and obviously everything extends to a continuous map on the closure. We're just going from the disk to itself, right? So this is great. As long as it maps the boundary onto the boundary, then we get that the interiors are the same. All right, cool. So this is just a consequence of the maximum modulus theorem, as we saw in the proof of that. So T maps D to D. But by proposition 5.2.1, the one we just looked at, this guy is also, since it's also a so this business right here, right? When we calculated these inverses, right? The inverse of a fractional linear transformation minus dw plus b over cw minus a. If we just go through and figure out what they are, notice we'll get, oh, I should put them all together. It's e to the I theta z minus c naught 1 over 1 minus c naught bar z. So just go through and put everything together. We get, now replacing our z's with w's, we get e to the minus I theta, since, the way to get rid of that piece is just to, put a minus e to the I theta times e to the I theta times e to the minus I theta is going to be what? E to the 0, right? Okay, so then all we get is w minus e to the I theta z naught over 1 minus e to the minus I theta z naught bar w. And this is exactly the same form as t. It's also a map from D to D, just because we just showed that maps of that form are maps from the disk to the disk. So t is conformal from D onto D. Nice. Okay, now let's do the other part. Let's let R from D to D be any conformal map. We'll let z naught be equal to R's pre-image of 0. Okay, so what z naught gets mapped to 0, or does R map to 0? Okay, and we'll let theta be the argument. I should use my highlighter here. We'll let theta be the argument of R derived at 0, or at z naught. So picture here, R sends D to D, so we've got some point that gets mapped to 0 over here, right? R is sending from, this is 0. There's some z naught over here that gets sent to 0, right? Okay, so z naught is the pre-image of that 0, okay. And we're gonna take a theta to be the argument of R prime of z naught. So at this point, derive R, evaluate it. What is that arg? All right. Now the map T defined in this guy also has T of z naught equals 0, right? throw in z naught and z naught minus z naught. That's definitely 0. Okay. So that also has t of z naught equals to 0. Okay. And theta is arg of t prime z naught, right? So, indeed, t prime of z, we just went through and actually calculated it. We can, since we're going pretty long, let's just take the book's word for it. Verify it on your own time if you'd like. It's e to the I theta 1 minus modulus z naught squared over 1 minus z naught bar z, that entire quantity squared. And if you put z equals z naught, very obviously you'll get z naught bar times z naught, and that is modulus of z naught squared. And so you just have 1 minus modulus of z naught squared over 1 minus modulus of z naught squared, so you just end up with a 1 over 1 minus modulus z naught squared. And I was right earlier, it's supposed to be squared. Okay, good. So all you have right there is e to the I theta 1 over 1 minus z naught squared. This is a real constant times e to the I theta. So from the nice uniqueness of conformal maps, this is the Riemann mapping theorem from what we were doing before. Let me go back to that. This f of z naught is 0. This guy's non-zero. It's unique, we're claiming, right? This is unique. So r is equal to t. All of the maps from the disk to itself, the nice conformal maps, any conformal map from the disk onto itself is a fractional linear transformation. And in fact, any transformation of this form is a conformal map of the of the disk onto itself. Nice. Nice. So this is the only way to map a disk onto itself conformally. It's the only way to do it. Fractional linear transformations are thereby important for being the self maps of the disk. There are also some other more nice additional properties that are pretty cool, and they are useful to talk about and will give us a lot of good stuff. So I think this is maybe a good place to end this one. Let's see. Yeah, it might be an okay place to end this one. Might mean we have to... Yeah, we have a fair bit on this left to go. Yeah, this is a good place to do it. We'll get into some more properties of fractional linear transformations next time, and we'll see just how far. Well, actually, no, we're going to be okay. We'll be all right in terms of the schedule because we have one more day budgeted for 5.2 next Monday, and then we'll have 2 days for 6.1, which is a cool section. And then we'll be done with this whole class, which is amazing. That's wild. 6 is the one that I really want to get to. 6.1, it's just neat. You guys will like it. It's pretty cool. It's sort of one of like the best parts of complex analysis, and I can't skip that part. So we're running pretty good. I think we'll be able to finish this one on time and really give 6 the attention it deserves. We'll have enough time to finish this and maybe do a couple of examples next time. But really, all you should think about with this whole fractional linear transformation bit is just that is just this little breakdown. Move it, flip the sphere inside out, do like that 1-point perspective thing, this homothety, and then move it again. That's all. Homothety plus rotation, right? And yeah, that's the business. So call it quits for today. If you have any questions in your homework, please ask me. I know everyone was busy with the exam. If you're feeling suffocated by this class, we're also at the end of the class, so I'm fine giving some. I know everyone's busy. If you need extra time on the homework, just let me know, and it's totally okay. So yeah, awesome. Have a great night.